Good morning to all. My name is Mahendra Rotela. I am a PhD scholar at Indian Institute of Science, Bangalore, but currently I am working in Purdue University on a scholarship given by Government of India. So I am working with Professor Daik over here, but in India I was working with Professor Gopalakrishnan, and this work I'll be showing as a part of collaborative work, which is on deep generative models for unsupervised delamination detection using guided waves. So let me start the presentation. So composite materials are dominantly used in aerospace structures because of their lightweight and high strength criteria. So, but what happens, these composite materials are complex in some or other ways, due to which what happens, there could be microscopic as well as macroscopic damages like fiber fracture, matrix cracks, which leads to delamination in the end. So what we have to do is, like, whenever there is a delamination, it is barely visible. So you can't deploy a computer vision kind of a technique. And the excitation frequency of an aircraft, or the actuation, the natural actuation of an aircraft is of order of few hertz. So you can't detect the damage via ambient dynamic vibration that happens in bridges. So you have to come up with the techniques which is a high frequency phenomena and can travel longer distances, where that's where ultrasonic guided waves comes into picture. So ultrasonic guided waves can travel longer distances with minimum energy loss, and it helps in inspecting larger kind of structures in less time. So what happens, you can deploy an actuator and a sensor, and when you excite a high frequency pulse, it interacts with the damage and your sensor captures that. So if you put multiple transducer, you can detect with accuracy. Why unsupervised learning? So in this slide we'll talk about the current trend. A lot of people have used supervised learning. So what is the difference between manual feature extraction, supervised learning, and unsupervised learning? So what happens in this current stage of the technology, digital sensors are increasing every day, and they are getting cheaper and cheaper. So what is happening, the data set which we are getting is increasing drastically. So what is happening with that, if you are using sensors to capture some signals, and you are using your manual features, like it could be statistics based, that is like mean, median, or it could be like a little more complex, like root mean square difference, correlation factor, energy of the signal, or spectral energy. Somehow these are manual features, so that restricts your damage detection ability when you are using manual features. So that's where supervised deep learning came into picture. So supervised deep learning, or any deep learning technology, is very good with automatic feature extraction with different level of abstraction. So their natural tendency is to extract features at different level of abstraction. How they do it is by minimizing a certain loss, and there is a lot of literature about that, and this I won't be discussing entirely. So what is the problem with supervised learning is, they demand first well labeled data set. There should be a label corresponding to every signal, and they should be balanced data set. There should be a presence of a balanced data set. It means the damaged scenario as well as undamaged scenario, the number of them should be same, or it should not be much more fluctuating, like 10:1 ratio. Here comes the use of unsupervised learning. How can you label something? For example, you're collecting a lot of tons of data for 10 years on a bridge. Now you have to waste 1 or 2 months to label it. So it is not possible to label it. It is time consuming, costly, as well as cumbersome. So that's where unsupervised learning comes into picture, when you have data sets which are not labeled. Another problem with unsupervised learning or supervised learning is balanced data set. So some of the application which we see right now, which are in the model, we are going in the model phase, like nuclear application, SHM for nuclear application, SHM for aerospace, outer space habitats, space station. These are data scale application. What I mean by that is, when you construct a nuclear reactor, you don't produce multiple of them and hit each one of them and to get all the possible damage scenarios in some ways and then train your supervised learner, because now you have seen all the damage scenarios. For aerospace application, you won't be getting damages in the initial stage. You can't produce the damage in the labs, similar to outer space habitats and space stations. So what we have is called a data scale scenario. It means first of all, we don't even know what are the damages and they are unavailable. So the uncertainty around the damages itself are much high. So what is the use of supervised deep learning in those scenarios? Unsupervised learning comes into picture. However, in unsupervised learning, we'll be talking about one class anomaly detection problem. So what happens in one class anomaly detection problem? You have only one class. Like with the current application I have shown, we can not get all the damage scenarios. So why not to just train on what you have? We have a huge amount of baseline data. So we'll be having a baseline data, we'll be training on that, and we'll learn the distribution and baseline signal, and we'll use the very basic technique, putting a threshold, and you have learned the distribution, you will put the threshold, and anything beyond that threshold will be classified as anomaly. So this will be the automated stage. After that, once it has classified the anomaly, there comes the human in loop. So for such application, there should be a presence of human in loop, because it costs a huge amount of money if anything gets wrong. Apart from money, it involves safety features also. So to learn one class anomaly detection problem, deep generative models has shown in computer science much more effectiveness to learn one class anomaly detectors. So what we are doing in deep generative model, two prominent techniques are there, GANs as well as variation autoencoders. We will be talking about only variation autoencoders over here, and GANs will be a part of our future work. So what are variational autoencoders? So autoencoder basically it has a encoder, it has a decoder. So you put input and output the same, and it learns the latent representation, which is a lower feature representation of the data set. So what happens in autoencoders, it doesn't learn a continuous distribution. So what you do, you want to push this latent space towards a particular distribution. So you use variation autoencoders. What happens, this prior, so the latent space is called a prior in Bayesian language. So when you have this prior, you push it towards a Gaussian distribution. So that's what makes variation autoencoder to learn much more better representations of the data set in a continuous form. That's why when you have something of a continuous distribution, it could be used very good with generative to generate the new data. So that is not our objective to generate a new data. Our objective is to learn robustly that governing distribution of baseline signals. So apart from a mean reconstruction loss, which we have seen in different unsupervised learning, there is a KL divergence loss, which pushes the prior towards a particular distribution, which is of a Gaussian nature, which makes it tractable in the end. So the strategy is very simple. You have a loss function. You minimize the loss you train only with the baseline signal. You minimize the loss unless it converges. Once you have minimized the loss, you capture all the errors, which is the sum of mean square error as well as KL divergence loss. You put the threshold based on your knowledge of the application. So we'll be putting two different thresholds to show their effectiveness. And then if you put a test signal in the entire trained network, if the error is more than the threshold, it is anomaly, else it is not an anomaly. So dataset is a well-developed dataset, well-developed benchmark dataset. It is a dataset which is captured on carbon fiber reinforced polymer. there is a quasi-isotropic layup, and we have used 12 different transducers and multiple frequency, excitation frequency, and different damage positions. So it's a well benchmarked data set which is we have used in some of our works, and it is available on Open Guided Wave benchmark dataset website. So before going into, we have raw time series 1D signals. So what we are doing a pre-processing featureization using time frequency analysis. So time frequency analysis is a technique which is necessarily not time domain, not frequency domain. Frequency domain is using FFT. It is plotting time versus frequency together. So this is called time frequency analysis, and one of the technique for time frequency analysis is continuous wavelet transform. Continuous wavelet transforms are much used in signal processing domain, and we have used over here. As you can see on the figure on the left hand side, you can see how the time domain signal looks like, and you convert them into time frequency. It looks like an image with the RGB component, and they are very good to train any possible CNN based networks. And they are why we are using wavelet representation. What is the use of this? This is available in one of our paper. So let's talk about the results. So as you can see in this figure, on y-axis I am showing the overall error when I push new test set. It means the network is already trained on baseline samples. We are pushing the test set, and on x-axis they are samples. So when I push new unhealthy images, it accurately classified as unhealthy, and I pushed new baseline signal is accurately classified as baseline signals in the confusion matrix. As you can see, there are two different threshold, and you can see two different threshold gives two different results. So unsupervised learning with any kind of autoencoder, you have to put a threshold. That threshold is decided based on your application, how much false negative rate versus false positive rate you want to do, and cost versus safety trade-off. So this threshold is decided by that. If you put different threshold, you will see different false negative rate versus different false positive rate. However, accuracy remains the same. So this is the latent space. The latent space is the crunch bottleneck layer. What happens over there? These are the all test samples. As you can see, unhealthy images are clustered at a point, and healthy images are clustered at another around some another location. So it shows in the latent space itself they are well separated. However, this well separation may not be possible for all possible complicated data sets. It depends on so many phenomena. Sometimes it will be so mixed. That's where the use of threshold comes into picture. How much false positive rate versus how much false negative rate you want to design your structure for. For example, I would say, for example, space habitats. So you don't want your, I'll give you an example of space habitat versus our regular home. As you can see in our regular home, there are so many false alarm with fire alarms. As you can see, sometimes it is just doing false alarm, lot of false alarm. We don't care about that. Even though don't the company care about that, because they know it's not a first level of safety. First level of safety is run out of the home. So there are possibility of false alarms in a fire alarm in our home. However, such thing is not possible with a space habitat. You can't afford false alarms because you can't go out. So it depends on the application what you want to do. What you want to do in terms of putting a threshold. So that's where the designers comes into picture. So in summary, we have shown variation autoencoders and its application to learn the distribution of baseline signals. We have shown how this framework fits very well with data scarce application where there are limited damage scenarios available to us. As a part of our future work, we will be deploying VAE on multiple data sets, and we are looking into generative adversarial networks and compare them with variation autoencoders. So thank you, and questions.